Today I'll be telling you a little bit about the snow on sea ice measurements during the MOSAiC expedition. Most of all have probably heard about the MOSAiC expedition before. I'll give you a quick overview after that afterwards. I obviously have many co-authors, some who are listed here, some who are not listed here, and I'd like to thank all of those. So just to start, where does the motivation come from? We obviously know what the current trends in the Arctic, in sea ice are, and especially in the Arctic sea ice are. And if we see these four figures, these figures show the northern hemisphere, the trends in the northern hemisphere. These two figures show the trends in the southern hemisphere. And what I'd like you to take from this slide is that the sea ice concentration trends in the Arctic are encompassing the whole of the Arctic. If you look at in summer, if you look at the winter in the Arctic or generally in the Antarctic, lots of it is at the periphery, whereas in the Antarctic, whereas in the Arctic, sea ice is declining everywhere. And that's, that has really big implication for future temperature projections. On this slide here, you can see the latitudinal temperature change projections for the end of the century compared to the beginning of the century. And you can see that the uncertainties in the Arctic are really, really large. And what we wanted to figure out, what MOSAiC wanted to figure out, is how to reduce these uncertainties and how also to reduce the uncertainties in the Arctic and how they will reduce the uncertainties in the rest of the world. In this presentation, I've structured this in 4 chunks. The first section will give you a quick overview of the MOSAiC and especially of the snow measurements of MOSAiC. The second part will look at some microstructure of snow during Lake 5, so during the last lake of MOSAiC, and I'll show you some really exciting results we have showing surface hoar and rain on snow events and how those relate to albedo. The third part will be about the spatial variability of the surface, so snow on the surface scattering layer on sea ice, and how that spatial variability changes in the freeze-up phase of MOSAiC, again during Lake 5. And the last one will really be a quick overview of the methodology where we use structure from motion photogrammetry to infer small-scale surface roughness. So let's start at the beginning with the snow measurements of MOSAiC. Most of us, when we think of snow measurements, is probably snow scientists stuck with their head in the snow and digging snow profile, which is also part of what we did. First, to go a step back in case you haven't heard about MOSAiC. So MOSAiC was the really big expedition the last year, started in 2019, for a year where the Polarstein was frozen and the ice for a year. And the idea is to measure all energy and mass fluxes between the ocean, atmosphere, and the sea ice, including biogeochemistry fluxes and the influence on the ecosystem. The expedition started on October 4th in 2019. The Polarstein was frozen in the ice. The different colors are the different lakes. So when the crew and scientists were exchanged, so this was in the beginning, and then this was the drift. The really big green chunk was where there was obviously no exchange because of COVID last year. This is Lake 4. At the end of Lake 4, the Polarstein melted out of the flow because it had drifted way too far. Then we went back into the ice, and I will show you mostly results from this purple from the 4 weeks in the last phase of MOSAiC. So snow, why snow? Well, snow is a key component in the energy budget of sea ice and plays an important role for sea ice prediction because it influences the energy balance through the albedo as well as through thermal conductivity. It influences ecosystems through light availability, and it influences remote sensing retrievals of sea ice. You can see in the left here is this picture for Matthew Sherman Massam from 2017. You don't have to look into this picture in detail. I just want you to acknowledge the really complicated processes that are going on in snow on sea ice and on the sea ice surface. And these processes are really important. I'm sorry if you can't see this, I can't quite move it. Are important for so we need to understand snow so we can have better projections of Arctic sea ice changes, so we can have better projections of temperature changes by the end of the century and further on, and also so we can have improved satellite retrievals, which are a really good estimate of what snow is of sea ice conditions today. So this is the beginning of that leg 5, of that last leg of MOSAiC, and it shows about a month. Let me just try if I can move this point. Okay. Sorry about this. Okay. And so this is showing the these are images of the flow, of the ice flow. The Polarstern is down here, and you can see at the beginning when we arrived, there were lots of melt ponds. There's a ridge along here, and at the end when we left, there was snow. It looked like there was a lot of snow, but actually, and on the ground, it just looked like white. But when you look from a little bit higher up, we can see that many of those melt ponds are not covered. So what we did was we used quantitative measurements of snow and ice properties because we needed those measurements to be reproducible and to be kind of the same for all lakes because we exchanged scientists. So obviously we did the snow profile. We looked at, we measured density and snow water equivalent and temperature. We had a micro CT on board where we looked at the microstructure. This is an image from a snow micropenetrometer. I'll talk about this later. And then this is a near infrared image where you can see the surface scattering layer at the bottom profile and the new snow on the top. I did this slide for an outreach blog, and you can see all the different things that we use in our measurements. So I'll now come to the part of science. This is the so I'll be talking about the microstructure of snow during leg 5, from surface hoar to rain. And I'll start, I'll start with again with the same image in the background, and here you can see some of the microstructural properties of the snow over the sea ice and what we've observed. So at the beginning, we had this surface scattering layer, which is essentially the melting sea ice at the surface with a really coarse anisotropic structure. Then at one point it started snowing, and you can see the difference between the snow and the surface scattering layer here is relatively high, even if the surface scattering layer looks like snow. Then the pond started freezing. Here we can see lots of air bubble, and down here air bubbles and brine channels in the ponds. We had some more new snow, surface hoar, and a relatively large rain on snow event. This is how the flow looked by the time we left. So it looked like a decent amount of snow, but as you can see, it hasn't covered up everything yet. So in the next few minutes, I will first talk about this bit about the different surface deposition, and then I will talk about the rain on snow event and how both of these events affected the albedo. So during this time, this is only within 4 days, we observed 3 different types of surface hoar, surface deposition. Above here are the actual images, how it looked like. Here we had these cups. Then on the 11th, I think then it snowed on top. On the 11th, we had these huge crystals of surface hoar. And on the 12th, all these surface hoar were rimed up. Now, how does that look for the albedo? So this is the 8, the 11th is up here, and the 12th is down here. So we can see that the albedo really jumps up when we get these large surface hoar structures. But when these structures rime up, the albedo changes, and even more in the long wavelengths. Now, the next thing I'll be discussing is the rain on snow, which just happened after those surface hoar depositions. And here you can see micro-CT profiles of the specific surface area on the left and density on the right from 5 snow pits before and after the rain on snow event. The rain on snow event happened on September 13th, 2020. And you can see that before the rain on snow event, here we have a density of around, close to the surface, of around 150 kilograms per cubic meters, which then goes into around 400 to 500. If you look at the specific surface area, we have relatively high specific surface area when we have these surface hoar crystals, which then, this is the beginning of the rain. So we've got the top layer is soaked through the rain, and then a day later, it's a really low specific surface area. And how that looks with the albedo. So up here, we have these surface depositions and new snow. And once it rains, the albedo goes down relatively fast. So what we can get from this is an extensive data set of physical snow properties that we can use to improve sea ice energy balance, albedo and albedo modeling in the Arctic. We can also use that for this data set for modeling of the thermal conductivity. The next thing I'll be talking about are the changes in spatial variability of the snow and surface scattering layer thickness, again in the leg 5 of MOSAiC. This is just an example image, and I will mainly be talking about transects that we have these pits, and then we have transects that we've taken alongside pits to see what the spatial variability is. And how do we do this? To go from spatial variability profiles to probability density functions of physical snow properties. So we have these obviously really high resolution microstructure measurements at one snow pit at one location, but seeing that the sea ice has quite a high spatial variability, we essentially want to get here and to see how does the sea ice actually look spatially. So what we did, we used mostly the snow micropin. We use this on all legs of MOSAiC, which measures the penetration force at a really high resolution. So up here we have the snow depth and the force of the snow micropenetrometer. And so we went along profiles, sometimes every half a meter, sometimes every meter, and just measured this. And then from the snow micropen, we can infer specific surface area and density with the help of these micro-CT profiles, and then we can see what is the spatial variability of the microstructure. And this talk, because we haven't processed all of our data yet, I'll just be talking about the spatial variability in thickness. And so first I'll be talking about the spatial variability of the surface scattering layer and thin snow on the surface scattering layer. So no thick snow, not much wind distribution, essentially the melt layer on the surface and then a thin snow layer on top of that. So here on the left, we see the surface scattering layer. These are four different measurements from the same day. Some are from very short transects in a snow pit, some are from longer transects. But what I want you to to take from here is that the probability density function is mostly very similar, like can range depending on the energy balance of how thick that surface scattering layer is, but generally it has the same form. It's very similar if we have thin snow on the surface scattering layer. This is from two different dates. The blue ones are from the 25th, and the red and pink ones are from a day afterwards. And we can see down here that the PDF is relatively similar, although on the second day after the snowfall, obviously the snow is a little bit thinner. The picture looks different if we have a large snowfall event with wind that starts covering up the melt ponds. So here again, this is all from the same day. These are different transects and different snow pits all over the flow on MOSAiC. And we have some of them, like these pink ones, the red ones, they don't have, it's just flat ice. They don't have any ridges. They don't have any ponds. So they look relatively easy. But the bluish-greenish ones, have lots of melt ponds. Like this is snow covering a melt pond. This blue one is going towards a ridge. And you can see as soon as we start having more ridges, more topography and covering melt ponds, then the PDF of the distribution gets a little bit messy and we can't quite predict how that's going to look. So what I want you to take from this is all very preliminary. We haven't even evaluated a fraction of the data, but I thought it would just be quite nice to show you something along the lines. So the spatial variability of the thickness of the surface scattering layer and early snowfall can be probably described by predictable PDFs. However, the spatial variability becomes much more complicated if we have more snow that's deposited with wind, if we have snow-covered ponds and ridges. Now, the last section that I'll be talking about is small-scale surface roughness, so very small scale, and how we can use multi-point photogrammetry or structure from motion to extract that very small scale surface roughness that's relevant to albedo modeling and for remote sensing retrievals. And I will just really quickly talk about the concept because we aren't that far with data evaluation yet. So what we did, we had these little targets here. And we were just taking lots of pictures from different directions of the snow surface. This particular example is of this beautiful surface hoar that we've seen before when we looked at the albedo. And then we made essentially very, very small scale digital elevation models. And you can see here, ignore the blue one, but you can see here we have a digital elevation model. It's about 50 centimeters across here, and has about 4 or 5 centimeters in difference. And we can see there's small undulations in the topography. We don't quite have enough image to capture those, like these ones, but we can capture the really, really small surface roughness. And the next I'll show you are 4 profiles that are every 45 degrees. So it's 1, 2, 3, and 4. And just to have a sense what the surface roughness looks in different directions. This is a this surface is not detrended. It's basically an elevation profile. And you can see this is about 2 millimeters between here and here. And you can see that we have a very high resolution surface topography that we can use. And if we detrend it, I know it looks a bit like a mess, but if we detrend it, we can essentially look at the anisotropy and look at the changes in surface, directional changes in surface roughness. Now we'll have to use a different method for this, like some use like a directional power spectrum to get azimuthal changes in surface roughness, but this is just to give you an idea what we can get. Obviously, not all images are this good because some of them, lots of them were cloudy. We have a lot of real surface roughness as well as the roughness of the interface between the snow and ice. So what we can get from here is that we can use structure from motion to infer these really small millimeter and sub-millimeter scale surface roughness for different applications, such as albedo modeling or remote sensing retrievals. I just couldn't resist to show you this image and this image as well. I'm here for any questions.
Thank you, Ruzica.